Today, as a speaker, we have Paweł Szczerbiak. Paweł is a postdoctoral researcher in team structural and functional genomics, which is led by Tomek Kościółek. And, Paweł has some background in computational and medical physics. He completed his studies at the Łódź University of Technology. So it was his bachelor level, and after that he completed his Master of Science and PhD degrees in theoretical physics at the University of Warsaw. And he joined the team led by Tomek Kościółek when Tomek was member of the Małopolska Center of Biotechnology. And now, together with Tomek, Paweł is at Sano Center for Computational Medicine. So he is interested in applying mathematical and machine learning techniques in general in science and in specific in this area of genomics. So, Paweł, screen is yours.
Thank you very much, Marian, for this nice introduction. Yeah, so before I move to the main topic of my talk, let me introduce our team. And as Marian said, it's led by Tomasz Kościółek, and thanks to his vision, passion, motivation, he created a very nice lab, a group with a great atmosphere. And currently the team comprises, or actually has comprised over the years, 5 postdocs, with 1 already graduated, Łukasz Szydłowski, who is pursuing his career in astrobiology, 6 junior researchers, with 2 also already graduated, Zuzanna and Mary, that are continuing their career abroad, and 15 collaborators, including students, people affiliated with our team and research assistants. So this is a moderated large group, but we have external collaborators, including many groups in Poland, of course, in the European Union, in Europe, like Belgium, Switzerland, Germany, and Estonia, and also in the US, including University of California, Davis, LBNL, and Emory University. And we've also collaborated with scientists in New York, University of New York, and Fraternal Institute. When it comes to outcomes, that is like the most important thing when it comes to assessing our work. Since its inception in 2019, so that was actually the time that I joined the team. So the group has released 32 peer-reviewed papers, and among which 15 have been led by Tomek itself. And since we joined Sano, we've published 12 peer-reviewed papers, and overall we've published 11 papers as a team, of course, not me personally. 11 papers in Nature portfolio, coming from Nature portfolio, so from the top tier journals, and in general we've gathered thousands of citations so far, which is very nice. Of course, the group and Tomasz personally is very successful in obtaining grants, including NCN, NCBR, NAVA, and FNP grants. So this is more or less what we do and what are our outcomes. And moving to the main topic of this presentation, so the protein function prediction. The concept of protein, I think, has been already discussed many times during other SanoSeminars, so you should be pretty familiar with this. This is like a biological entity comprising of so-called residues. Okay, so here we have two examples of alpha helical proteins with those residues building this entity, and these are just like a group of atoms in the 3D space, and we call them residues. This is a convention. When we speak of a protein sequence, we just encode those. They're actually encoded as amino acids. So this one-to-one correspondence between amino acid and residue. This notion is important because I will use this later. Yeah, so we have those proteins as inputs, like general, like conceptual proteins as inputs, irrespective if this is protein sequence, protein structure, or some other derivatives or descriptors of a protein. And the goal is to predict their functions. And this is a bit elusive, in my opinion, because there are different classification systems of protein functions, different approaches to that. For instance, here we see a hierarchical representation of one concept. So we have some specific function out there and their parents, and this is like it builds hierarchy. And this is the most widely used hierarchy in protein function prediction. It's called gene ontology, and this is because we do have a great databases with a lot of annotations of proteins using this hierarchy, this classification, and that's why people use this. And we also use this in our predictor. But there are other systems like Brenda, Enzyme Commission, KEGG, CASI, COG, or we can also predict functions using free text descriptions. So the problem is tough. It's not definitely straightforward due to many reasons, and this is one of the most important reasons. Simply, it's hard when it comes to the output. And yeah, there are a couple of approaches on how we can talk about projects we are working on. One is a problem-based, second can be like history-based, and what I will actually describe the project I'm working on using the second, using the latter. So here is a timeline, and I will be like showing you the project side projects and projects regarding the deepFRI ecosystem on the time also using this timeline, this time scale. And deepFRI started, I think, during COVID time in 2019 or even before. Tomek probably remembers better. So deepFRI stands from Deep Function Residue Identification. So this is a system that identifies residues, so those amino acids in 3D space that are responsible for specific functions. And so it directly utilizes protein 3D protein structure. And it's been published in 2021, and of course with Tomek as one of main contributors, and it garnered a lot of attention. It's been cited almost 1,000 times so far, and a lot of people use this. So it's pretty successful. That's why we want to continue. When it comes to architecture, there are two modes in which we can run deepFRI. First one is sequence-based, so it just utilizes protein sequence, so amino acids. It's then straightforwardly encoded into one hot feature matrix that is then processed with a convolutional neural network. And that's and then there are of course certain post-processing layers, including dense layer and sigmoid activation, thanks to which we can get pseudo probabilities. So this is a vector of probabilities or pseudo probabilities, if we want to be more precise, of this protein having a given function. This is like a flat vector, and each index here corresponds to different function. And so this is an inherently multi-level classification problem. So we predict undefined number of classes, which is harder than like this usual multi-class problem. And there are 4 independent neural networks in this system. So one for each ontology, molecular function, biological process, and cellular component for gene ontology. And the fourth is a little bit independent, is somewhat related to MF, but this is a tree-based system, enzyme commission system. So there are 4 neural networks out there. And the second mode is structure-based prediction. When we put a protein structure this time, is then encoded into contact map that shows you which residues in 3D space are close to each other, okay? And then it's processed with a sequence of graph convolutional network layers. There's a GCN block, which utilizes also a sequence signal. And this is processed with LSTM that was retrained with PFAM database, and then the signal coming from LSTM is used as a first adjacency metric. It's actually adjacency. Sorry, it's not adjacency metrics. This is just a first layer of weights in this GCN block. Because adjacency matrix is built using this context map. And similarly, there's a dense layer, so there's classification layer and sigmoid activation that gives us pseudo probabilities. And the same as in the sequence-based mode, there are 4 independent neural networks. And this architecture is pretty robust, or at least was robust at that time. So we wanted to use this and retrain deepFRI using AlphaFold DB that appeared in in 2022 or 2023. So in 2023, we just wanted to use it immediately after it appeared. And of course, we used also the gene annotation database that is powered with the UniProt database. We imposed certain quality controls over those databases. And in total, we've used almost 3 million of protein structures, so 10 times more as in original deepFRI1. This is a lot that had been annotated with almost 60 million of annotations when we use this Go hierarchy propagation. So we utilize the whole hierarchy of gene ontology. This is a lot of data. As I mentioned, we use the same architecture as in the original deepFRI1 because it's been thoroughly tested and reliable. So we just wanted to change the training set. And we extended the gene ontology coverage 3 times. So instead of predicting like 3,000 of classes, we're able to predict 9,000 of Go terms. This is a huge increase of functional units we can predict. And at the time of testing this, evaluating the deepFRI1 performance, everything was quite fine, including the calibration. So how the precision or recall or whatever measure we want to use looks like versus the deepFRI score. So the threshold at which we select or filter high quality prediction. So the calibration was okay, but the problem appeared when we wanted to assess the robustness of those predictors on some reference database, which was MIP database, Microbiome Immunity Project database, if I remember correctly, but we also tested it with other databases like AlphaFold and TSM. This is probably the MIP database, if I remember correctly, but the results are quite similar also for the other reference databases. Long story short, irrespective on the database, if it is large enough, the outcomes are quite similar. And so this was actually done with Łukasz Szydłowski with his manual translation of gene ontology into clusters of orthologous groups of proteins, so the COG in short, the COG classification. And there are 3 categories in COG, so cellular process and signaling, metabolism, information storage, and processing. It turned out that for those references databases, deepFRI1 predicts balanced predictions, balanced outcomes. So the proteins in those databases are covered with all those 3 crucial functional categories. whereas deepFRI 1.1 was not as good, and the predictions, although there were more of them in total, but they were not so well balanced. That was a problem, and so we actually abandoned this side project. We wanted to reevaluate everything and go for deepFRI2, which I will be talking about quite soon. But we learned a lot with this retraining, and if I were to use this to do that one more time, I would just retrain it with a constant feedback. So go back to the training process, to quality controls, reevaluate everything, and then train the model one more time. So that's actually the most important lesson we've learned from this. So test your model robustly. Yet another project within the deepFRI ecosystem is called, so the software is called Metagenomic deepFRI. It's been initiated by Tomek. So it was his idea to train this kind of software. It's been coded originally by Piotr Kucharski in 2022. Then it's been redesigned with the help of Valentin in 2024, and then took over by Filip Szymik. And finally, we released a preprint quite recently this year. And what this is about? This is about utilizing deepFRI with the structural mode, but utilizing sequences as input. As input. So the software, using homology search, finds structures for a given input sequence on the fly. And it scales quite well and can be used with metagenomic setups for metagenomic database. And one more side project. It's called Free Data. This is actually quite tightly bound to deepFRI2. It's been developed by Adam Nowak under my supervision. This is about creating training data for deepFRI2 in a non-redundant, scalable fashion. So once we provide a list of IDs, so just a TXT file with protein identifiers, it creates a dataset or template for a dataset, extracts sequence for each protein, create embeddings, extract coordinates, create histograms, and other derivatives. This is quite robust when it comes to extending the list of derivatives we can create based on for a protein. So this is just a sketch of this. This in reality much more complicated. There are much more features in this. I don't want to talk much about that, but long story short, we do have a very nice setup for training deepFRI2 thanks to this free data software. This is ongoing. We are gonna release it on PyPy in upcoming months, probably, or weeks. Yeah, so now moving to the main point of this talk, deepFRI2. This is our goal is not to solve protein function prediction problem. There are many reasons for that. One of them I've already covered, so this is not well stated problem. But we can somehow alleviate this and like just utilizing gene ontology or some other classification. But the problem is that even in gene ontology, we don't have enough data. We do have this fantastic gene ontology annotation database that is well structured, and we have a lot of metadata out there, so we can train the model quite robustly. But the problem is that only 1/3 up to 1/2 of gene ontology terms are annotated with just one annotation. So the problem is that we cannot actually reliably predict all gene ontology terms because of lack of data. And another thing is that our inputs we are using are actually probably obsolete at the moment. I will go to that point later on at the end of my talk, because we are just using a static 3D structure for that, and there are probably a lot of functions that cannot be reliably predicted just by using this single protein. And yeah, another point is that there are already quite precise predictors on the market that are giving good performance, or excellent, in some cases excellent performance, for some specific applications, for instance, like enzyme activity or whatever, because they utilize atom resolution. We are not going to use atom resolution here. We are just using the residue level, okay? This is a different layer of information. We are not as precise here. But the drawback of those methods is that they are usually either giving great performance for some very narrow applications, or they are simply slow, or both at the same time. It's always like that. There are certain pros and cons of each model, each software. And last but not least, we do have limited resources, so we cannot afford for training huge systems like AlphaFold with hundreds of GPUs or whatever, and also our team is not as big. So this is not our intention to solve this problem. This is infeasible, in my opinion. Rather, I personally am interested in understanding how small model we need for a decent, meaning that like comparable to state of the art, for decent protein function prediction. And there are two other like sub-objectives, sub-goals. So what can we learn from it for the future? And the original idea behind deepFRI2, that is super important, is to create a scalable tool for metagenomic applications. And of course, all of that is tightly bound. And thanks to this, the fact that deepFRI2 is actually quite small, it can be both interpretable or explainable, but also it can also scale quite well and be used for machine applications. So the input and output are the same as in original deepFRI due to legacy, actually. So we use a single protein sequence and structure as an input and try to predict gene ontology terms. As I mentioned, this multi-level classification problem with 10 to 3 classes. As always, in such kind of systems, we do have two ingredients. First one is training itself. The second one is inference. And this is just a draft of how this looks like on a high level. So I've already covered those databases. So we just use gene ontology, Nipot, and AlphaFold data, and then it's processed with so-called data workflow. It's semi-automated, and then it is pushed to free data. I've already covered this software. And so we can actually generate arbitrary number of training sets. It's pretty scalable, and thanks to this non-redundancy. And then there is a data loader that extracts data from free data and creates the derivatives, numerical representation of proteins. That is then used by two ingredients of the deepFRI2 model, the sequence analyzer and structural prober. Sequence analyzer is powered with ESM2. So free data actually computes the protein language model embeddings, and we use ESM2 because they perform the best. And there is also a lightweight attention mechanism that is used to pull the embeddings, and it performs better than multi-head attention on whatsoever. It's super small, like it uses just 64 hidden units, which is very small but robust. So I'm very glad that it works like that way. On the other hand, we also have structural prober that works solely on protein structure and actually on distances between residues. There is a shallow convolution, so just one convolution over the histogram matrix, and then there are statistics that are computed based on the features coming from those convolutions. And there is also a fusion model that integrates those two independent signals. That is crucial. In deepFRI1, those signals were actually mixed. So you wouldn't say actually which part is more important for a given protein to have a given function. Here, this is separate. So we can speculate and say that, for instance, only structure matters irrespective from the sequence, or the other way around. That was important from the very beginning for me. And then we have a fusion model that integrates those two signals. I've already, so there is, I was mentioned about this fusion model. So this is also quite simple, quite straightforward. It just utilizes gating mechanism. Like gate is of course conditioned on some certain inputs. I will move to that part on the next slide. And last but not least, so we do care about simplicity and robustness. And that's a crucial in this project. A little bit more about the architecture. So this sequence-based prediction, as I said, is powered by ESM2. Then we have this attention pooling mechanism and quite usual post-processing block or head of the model with layer norm dense, rel dense, and softmax. Sorry, this is actually sigmoid. I should replace this. This is not softmax. This is wrongly written here, because this is multi-level. So we use sigmoid for each neuron, for each logic. We do also have the structural prober, structure-based prediction, where the protein is processed in a way that we generate a histogram. So this matrix showing the distances between residues, being a generalized version of contact map in deepFRI2. Then it's processed with Gaussian transform to have a similarity matrix. And then we use convolution with two sets of kernels, diagonal kernels and anti-diagonal kernels, that process different parts of histograms to get different features. After convolution, we gather statistical features like median, mean, top k, top k positions from a given kernel, and then we aggregate this and process with the with post-processing layers. The only difference with respect to the sequence analyzer is that we are using batch norm instead of layer norm because it works better in this for this model. And then, as I mentioned, those two signals are integrated into the final prediction with gating. It's just a sigmoid over dense over ESM features. So this is conditioned on sequence features. It simply works better that way. That's why we use this. And then we have refined predictions. Each step here is kind of explainable. We can, because those models are super small, like in total there are like a couple of million of parameters, like 3 million of something. So the model is super small, at least the molecular function. Okay, but I'm talking about number of parameters for the molecular function ontology. For the CC, it should be smaller, for BP larger. Great. So now, like speaking of features of deepFRI2, I said that we do care about simplicity and robustness. By simplicity, I mean interpretability and scalability. First concept, we can have both global and local interpretability in this setup, like in most moderately large machine learning systems, and scalability. That's crucial for machine learning applications. Thanks to the fact that the model is small, it scales pretty well. Yeah, when it comes to robustness, it's so this basically testing, and we test this comprehensively, like utilizing temporal holdout, out of distribution sets, and residue level benchmarks. And when it comes to the potential applications and extensions, I also want to have like easier training of deepFRI2 and fine-tuning. And when it comes to additional features, we do have free data as a separate ingredient of this ecosystem. I would also like to create deepFRI2 development kit to ease the retraining and fine-tuning procedure. And we'll also try to integrate go to other ontologies mapping to make the outputs more robust, so we can just not only predict gen ontologies, but also translate them into other systems that are better for other use cases or for some specific application. And we also try to integrate to train not only general purpose predictor like deepFRI2, because this is actually general purpose predictor, but also go for eukaryotic version and metagenomic version. It all depends on the data quality. So this is ongoing. Because we are currently at the stage of finalizing the architecture and the molecular function module. Then we go for CC and BP, and then try to generalize it for other use cases, so eukaryotic and metagenomic version. Actually, not generalizing, but specializing, to be more precise. Okay, so when it comes to interpretability, so I mentioned that we can have both global and local, and by global I mean we can of course use attention scores because we do have attention in sequence analyzer, and it works pretty well. It all depends on how large attention you are using, because our is lightweight, it's pretty robust, and it seems that the outcomes so the attention scores have some biological meaning, but this is ongoing. And the structural prober also reports kernel attributions, so we can just gather them and also have this a global signal, interpretability signal. And there are three such attributions, so the diagonal, anti-diagonal, and the sum of those two. And when it comes to local interpretability, of course, we can use gradient-based measures, so the vanilla gradient, input times gradient, integrated gradients, or more advanced techniques. In deepFRI2, developers used, actually the main author, so the Vladimir Grigorievich, he used GradCam, and which was a good, very good decision. But it's not so that GradCam or GradCam++ is always better than, for instance, vanilla gradient or whatever else. There are papers showing that it all depends on specific tasks, okay? So in some cases, GradCam is better, but in some cases, vanilla gradient is superior. So we should always like test everything and not go for the most advanced or the recent solution. Here I'm showing you the comparison between the global attribution attention scores and gradient-based feature for some specific protein plus Go term pair. So this is sequence analyzer signal, and the vertical lines, so those spikes, are ground truth residues, and the signals themselves are coded with blue, green, and red lines, respectively. So this is just an example, and we are working on that. But in this specific case, it seems that there is a quite nice overlap between our global and local attributions and ground truth. And here we have a different scenario. So this is a structural prober signal where we have only those, like in this case, we only have local attributions and encoded with different color. And so here we have just ground times input sign version, absolute version, and diagonal part and anti-diagonal part. So yeah, maybe I should also talk about the difference between diagonal and anti-diagonal part and those kernels. So mainly the diagonal kernels capture the signal coming from the main chain of a protein, whereas the anti-diagonal part that actually probes the upper triangle of a distogram capture the distant contacts. And in this particular case, the distant contacts produces some false positives. So the function would be probably more interpreted just by using the main chain residues. That's what we can learn from this. But this is ongoing. We are working with the more robust setup, and the main contributor of this is Rune Tafik. And when it comes to testing our software, I mentioned that we have a couple of different testing sets. The first one is the most straightforward, so this is just temporal holdout set. And the deepFRI, so here we have, to the left, we have F1 score versus the threshold. So the deepFRI score, on which we filter the high quality predictions. And to the right, we have these usual precision recall curves in general, because we have more than one predictors. And deepFRI2 is encoded with blue, and the other competitors are predicted with other colors. And in this particular setup, deepFRI2 is better than the other competitors. And the same concerns the out-of-distribution set, so the CASI dataset that was designed by Łukasz Szydłowski and Jakub Wojciechowski. And the same story, so deepFRI2 generalizes quite well to this out-of-distribution datasets, in particular the CASI dataset. And third benchmark that was created by Rune Tafik is protein ligand binding. So we have 10 different ligands, and here we have a coverage to the ground truth of our predictors, so the final model, the ESM, so the sequence analyzer, and the structural prober. And we also have for reference, so the deepFRI2 model. And in 9 out of 10 cases, like excluding ATP, deepFRI2 is superior to deepFRI1, which is a good sign. But this is also ongoing. So the performance of structural prober is not very satisfactory in this task. We will try to boost this by using the chemical properties of a sequence. And that was the idea proposed by Jakub Wojciechowski. I would like to integrate this also in our system. And yeah, so we're living in a quite exciting period of structural bioinformatics. And it was started, I think, with the AlphaFold 2 revolution. And thanks to the competition between the different tech giants, so Google, Meta, Microsoft, and other great papers appeared and great software appeared. And first of such is are the protein language models created by Facebook Research. So the evolutionary scale modeling models, so ESM models. And this is currently developed by evolutionary scale spin-out from Facebook Research. And we are using them because they are quite reliable, I would say, and well tested. But lastly, like Microsoft Research also appeared and started like releasing great software. One of such software is BioEmu that emulates or like predicts, generates not only like a single conformation states as in AlphaFold, but thousands of conformational states of a protein. So we can actually model dynamics of a protein. And like having all those great software on the table, we can utilize them. This is actually my grant proposal, so the NCN Opus grant proposal. And of course, we know that like getting funds from NCN is super hard. So this is not a project that I will be doing. I don't know that yet, but this is a putative proposal that can be done. So this is about like creating a next generation protein function prediction, the real one, where we integrate not only a protein sequence and static protein structure, but also the 3D protein dynamics, for instance, using BioEmu or similar software, and also the genomic context, because some functions are probably can be only predicted not only by utilizing just a single protein, but also its neighborhood. And there are a couple of ways on how it can be done. So the first work package was to create this next generation software, and then wrap it with a computational ecosystem, because we already have some experience in creating web servers and databases, to put it into a computational ecosystem, like creating a storage and web server. Last but not least, the third work package was about drawing biologically meaningful conclusions and implications from this, which is like that includes like better understanding the protein function relationship and stratifying this by the input. So which functions are more determined by sequence, dynamics, or context. And the crucial thing, if you want to publish such stuff in top-tier journal, is experimental validation. It's super important. And in this particular grant application, I also wanted to try to say something, like to verify some of the most interesting conclusions also experimentally. But this is of course super hard, and yet another story. Yeah, so that's all on my end. Thank you so much for your attention, and I would also like to thank my collaborators. So Run Tafik, Adam Nowak, Witold Wydmański, Jakub Wojciechowski, Jakub Adamczyk, Łukasz Szydłowski, and of course Tomasz Kościółek. Thank you very much.
Many thanks, Paweł. Well, it's very interesting proposal of new methodology. It would be interesting. What is your opinion about because with these new possibilities, I have impression that the part of let's say knowledge was shifted towards let's say automated way to process. And the question is, what will remain as let's say in hands of humans, and which type of knowledge will be still necessary and probably more important in this process?
Yeah, so like also in this particular project, I'm using AI agents that is like basically like heavily facilitate work with and speed up the training procedure. So very hard to avoid using AI agents for that such tasks. But at each step, I always like try to follow what actually agent generates, and this I think it's super important when it comes to the assessment of the outcomes coming from AI. So the critical thinking is something we shouldn't like actually like forget about. And what I also always like to use or integrate is like manually creating tests, okay? Just to not allow AI to test everything by itself. So once we design the whole process robustly, I would say, with a specific like splitting the project into parts and having those tests or whatever assertions on the way, then we can fill those remaining parts with AI engines with ease. So that shouldn't be a problem. So it's not actually like I'm actually not precisely answering your question because it's too complicated. I cannot tell you exactly what things would be important to uh, in general, but based on my experience, I don't trust AI at least currently. So I always try to use those assertions on the way.
Well, I think that the most important what you said was that critical thinking, but critical thinking is not possible in this area without, all this basic knowledge. So I think that it's you need it in order to be sure that what is proposed is reasonable. So yes. We have Olaf back. So Olaf, please.
Yeah, Paweł, I joined a little bit late, so maybe you have answered the question along the way. But I think one of the main problems in all this is that the labeling for functions leaves a lot to be desired, at least from a perspective of an AI training. Yeah, you have gene ontology categories, fine-grained categories where the appropriate master category is missing. You have certain implications that you know that a certain kind of functionality, enzymatic functionality, may require a certain cofactor, which you could use as kind of a proxy prediction in order to see whether that's true. And I wonder how you deal with that. Do you do click completion or kind of other label inference before you really train?
This is a great question. Yeah, so no, I don't. I just use this similar pipeline as was used in deepFRI1, and that was super easy in deepFRI1. There is just a one script that downloads SIFTs and PDB databases and train the model. And this is quite similar here. There is some pre-processing of annotations, but this is not yet manually curated. We should actually work on that more before we go for CC and BP ontologies, because for MF, it seems it works quite well, but this pre-filtering and pre-processing will be important, especially for BP. And again, I'm not sure because I'm not a biologist by myself, so I cannot comment so well on this particular the cases you've mentioned. But maybe we can come to that and discuss it with our more biologically oriented colleagues in the team.
Okay. Yeah, I'm also volunteering here. So of course, um, I think it's really important. Well, I was involved with Brenda for a couple of years, actually, with the enzyme database, and there's also what you want. I understand that for metagenomic purposes, what you want to do is you want to get a grip on the physiological capabilities of a certain metagenome. So what can it process, yeah, and what it can't. So I would argue that deepFRI2 is not yet at that level because you are not capable, in, as I understand, really to understand which, let's say, substrate bindings are really there, yeah, in the process. So you wouldn't be able to do a metabolic network just from the protein functions that you find in your metagenome. So I think that that's the overall long-term goal to some extent. So I was wondering, in your NPN proposal, there was in the work package 3, there was a side package about where in one of the corners there was KEGG, the pathway database. Yeah. So wouldn't there be another way to do it by starting from a pathway and interrogating more or less, is it probable that this pathway is present or absent? Because I think so far, I think we have a pretty good understanding of what, at least for many secondary metabolisms, we have a good pathway understanding. So we could just ask, is there a local, meaning a binding motif, or a global, meaning the same structure family, then an enzyme that represents this function of this pathway present or absent, and then we can try to perhaps interrogate the gaps. So if we find 6 out of 7 enzymes in a pathway, we would typically assume, well, the 7th should be there, or there is some kind of shortcut or something. So then we can go hypothesis driven into that question, what can this metagenome do? So isn't that a better way than doing it all bottom up, like this seems to be?
Absolutely, yeah. This is a great suggestion. So I would love to integrate other approach than just this straightforward gene ontology based. Maybe somehow like utilizing more than one protein as input. Okay, so just a group of proteins, and that was actually also the original idea of deepFRI2. So the initial idea was to first train the single protein model and then go for a context-based model that utilizes more than one protein as an input. And maybe we'll go for that in the near future. Maybe it's like doable, and also like this pathway-based approach would be also quite nice to integrate as long as we have enough data for that. Otherwise, we should probably like use the original procedure, but with some kind of refinement that integrates pathways on some like at some point. Okay.
Okay, coming back to my first question about, let's say, label augmentation, more or less. So what happens if you have, let's say, a training and something is not annotated as being, let's say, a lipase or something, and it would predict to be a lipase, yeah, then you would say it's wrong. So the scoring function would say it's wrong, the loss function, and would cast it as an error. So that should introduce class error, and class error is typically something where AI models are very sensitive. They are not sensitive regarding parameter errors, but class errors is something where they're really sensitive. So how do you deal with that?
I'm not sure if I'm familiar with this class error problem. So what I can say you is how actually the deepFRI2 is trained. So what loss functions are actually used here. So we just use this straightforward weighted focal loss. In deepFRI1 it was just cross entropy, weighted cross entropy. So this is just quite easy, like straightforward approach. But we also, like thanks to Jakub Adamczyk, that suggested to use the MCM loss. This is a little bit different when we actually have loss based on the difference in predictions for for a leaf and a parent. So the model is actually penalized when it predicts higher scores for the for the leaf and not for the parent. And it gives a better performance. When it comes to this class error, maybe we can elaborate on that during other occasion, like after the seminar, because I'm not if I'm familiar with this concept.
Okay.
It's quite interesting.
Well, Olaf, many thanks for your questions and for discussion. Well, I trying to find who is in the queue. Well, I see that there is nobody in the queue, so, well, it means that we should thank Paweł for very interesting presentation of his new, to some extent, new methodology, and Olaf for discussion. Thank you very much. And on the next week, there will be no Sano Seminars. It will be internal. Well, it depends on what our girls would like to present. Maybe it will be partially public seminar, but look for announcement. So many thanks, and see you in a week from now. Thank you. Bye.
Thank you. Bye.
Thanks.